Okay, so far we have seen the hypothesis testing and confidence interval. Specifically, it is actually for the one sample inference. Okay, so what we did is just the one sample confidence interval and the one sample test. So what is the one sample inference? Actually, one sample inference for me. So the one sample inference for me is when you have one sample, x1, x2, to xn, in observation from the population. This is one sample from one population. And the parameter we made inference on is the population mean or the true mean mu. So that's why it is called the one sample inference for me. There is a big population and we get one sample from this population and we want to infer some information about population parameter, which is the mean true mean of the population mu. And one last thing about the one sample inference is the prediction interval, and we will talk about the prediction interval in this video. And then there is a special kind of data called matched pairs data. So this is also an application of the one sample inference. And we will be talking about the inference for matched pairs data today. And then we will continue to the two sample case. So we will also start the inference for the two sample data, where we have two samples from two observations. And for both of these inference for matched pairs and inference for two sample data, the parameter we are interested is the difference between two means. So although the inference for matched pairs is actually a one sample inference and it is different from the two sample inference, but the goal are the same for both of them. They are both doing the inference for the mean difference. Okay. They are both interested in the difference. So the first thing is the prediction interval. Recall what we have for the confidence interval is this. Suppose we have n observations. This is our one sample. They are ID and with mean mu and standard deviation sigma. And if the sample size is small, we also have an extra assumption, which is the normality assumption, where we assume each of them is IID mu sigma squared. And then this 1 minus 1, 1 minus alpha confidence interval for the population mean mu gives us an interval that captures or brackets the true mean mu with 1 minus alpha confidence. So you can think of the confidence interval as some likely values for the unknown mu, because you don't know the true mu. So the confidence interval, for example, if the confidence interval is from maybe 0.5 to 0.6, so this interval provides you some likely values for the true mean mu with some confidence. So you can think of the confidence interval as some likely values for the unknown parameter mu. And the prediction interval is similar. So it also gives some likely values for some unknown new observation. So we use xn plus 1 to denote this new observation. It is unknown. We have not yet collected it. There is a prediction interval for this unknown new observation. But it is not called a confidence interval because xn plus 1 itself, it is not a parameter. It is actually also a random variable because it's a new observation. And remember, a parameter is unknown, but it is a constant, so it is not random. So there is a very big difference between the prediction interval and the confidence interval. The confidence interval is just for some unknown constant when we call it parameter, and the prediction interval is for some unknown random variable, some unknown new observation. And to construct the prediction interval, we will need the normal assumption. So we will assume data from a normal population with mean mu and variance sigma squared. And we have x1 to xn independent from a normal distribution with mean mu and sigma squared. And the new observation is also from the same normal population with the same normal distribution. It is also independent of the other observations. And we will assume that both sigma and both mu and sigma squared, both of them are unknown. Okay. So these are the 1 minus alpha prediction intervals. You can see that we also use S because sigma is unknown. And for the prediction interval, we use the quantile of t with n minus 1 degrees of freedom. And if you use a two-sided prediction interval, then you will use the 1 minus alpha over 2 quantile. And if it is a one-sided confidence interval, then you use 1 minus alpha quantile. The difference between the confidence interval and the prediction interval is we have a 1 in the square root. So in the CI, in this part, everything are the same x bar plus tm plus 1 and times s times, in the ci we have just the root of 1 over n, but in the prediction interval we have a 1 plus. So this means that the pi is wider than ci. Why? So this is also making sense because the pi is for a random variable, so it should be wider because a random variable is there's more uncertainty in the random variable, right? The confidence interval is just for an unknown mu, but the prediction interval is not only for an unknown mu, it also for unknown new observation, and that new observation has an unknown mean mu. So it should be wider because it is a random variable. So it is wider than Ci due to more uncertainty. Because there is an uncertainty in the mean mu, and also there is an uncertainty in the deviation of the observation from the population mean. So there is a more uncertainty, which makes you prediction interval wider than the confidence interval. And if the sample size n is large, and then you can also use z instead of the t quantile, same as the confidence interval. So I will not do more examples of the prediction interval here. Check another prediction interval video on Canvas for more examples. So it is a rather short video, about 20 minutes. So let's see the important thing, the interpretation of the prediction interval. So the interpretation of the prediction interval is similar to the interpretation of the confidence interval. For the confidence interval, our interpretation is if we repeatedly if we repeatedly get one sample from a population and calculate the confidence interval, eventually, if we repeat it thousands of times, then if we are constructing a 95% confidence interval, that means out of this thousands of confidence intervals we obtained, 95% of them will capture the true mean. Same here for the prediction interval. We will repeat the following process many times. So we get one sample from the population, and there are n observations in the sample. Then we construct a 1 month alpha prediction interval. So in this case, for example, we are constructing the 95% prediction interval using this one sample. And then we collect a new observation, xn plus 1. After we repeat this process a lot of times, thousands of times, among these repetitions, then 95% of these prediction intervals will eventually contain the new observation. Okay. That's why we say that we are 95% confident that the prediction interval contains the new observation, because we know that over a lot of repetition, then eventually 95% of the prediction intervals will contain the new observation. So you know that. So from this interpretation, you should know that the constructed CI or PI are not random. Okay, it either contains, for the PI, it either contains the new observation or not each time when you construct the prediction interval. There is no probability involved. The reason we say that we are 95% confident is that we know if we're repeatedly using this method to construct a prediction interval, then 95% of these prediction intervals will contain the new observation. Okay, but for a single prediction interval, since we don't know whether it contains the new observation or not, we just say that we are 95% confident that it contains the new observation. Okay, that is for the prediction interval. And then let's see the matched pairs dataset. So the matched pairs dataset is a special kind of dataset where the measurements can be grouped into pairs. In other words, the observations comes in pairs. So this is what matched pairs datasets typically look like. So this is our data table. And there are two measurements. In each row is our one, there is a one observation. So there's a measurement called Y1 and a measurement called Y2. So for each observation, we have two measurements, Y1, Y2, Y1, Y2, Y1, Y2. So it's a table. If there are n observations, then it is n by 2 table. These are some examples of matched pairs dataset. Set scores before and after the prep course. So these two measurements are set scores before and set scores after the prep course. Severity of disease before and after treatment. So it's again a before and after measurement. Leading edge measurement and a trailing edge measurement for each workpiece. These two measurements comes in pairs. And bug bites on the right arm and bug bites on the left arm for a person. And because it is experiment, actually we have one repellent and the other arm don't have. So the measurements comes in pairs. It is a one sample inference because actually we only have one sample from the population, although we have pairs. So, for example, the set scores example. The population is all the students. And we got a sample of n students. And we have set score before and after a prep course for each of these students. For student I, we have two observations. We have two measurements in a pair. So it is score before and score after. So for each student I, we have a pair of measurement. So although it's just one sample, but for each observation in this one sample, we have a pair of measurement. So data come in pairs. Okay. This is just still one sample. So we will still do the one sample inference. And for the matched pairs dataset, what we are interested is in the mean difference in the two measurements. Okay. So to make inference about the mean difference, we will use the confidence interval or the hypothesis testing we have learned. Because the data come in pairs, so let's assume that we have matched pairs data like this. So if it's in a table, then it should look like this. In each row, we have y11, y12, y21, y22, yn1, yn2. So there are n observations, n pairs of measurements. And we will also create a new column. There is a difference. di equals y1 minus y2. Then we have a column of the difference of these two measurements. If we assume that these di's are ID, and also if the sample size is small, we need to also assume that di's are normally distributed. And also we denote the true mean difference is mu d. Then we can then use d1, d2 to dn as our sample to do the statistical inference, the one sample. One sample inference using d1, d2 to dn. Okay. So this mu d is the expected value of the difference di, the mean difference. So it is actually also the difference of the means, because by the linearity of the expectation, it is the expected value of EYI minus the expected value of EY2. So it is also mu1 minus mu2. Okay. So the mean difference and the difference of the mean are the same thing for the matched pairs data. Okay, so let's see an example. This is an experiment of the comparison of the fuel economy using two different types of tires. We have 12 cars. First, it is equipped with radial tires, and then the same 12 cars are again equipped with the regular belted tires. The same drivers are used, and then we record the car's gas economy. This is our data for each car when it is equipped with radial tires and it is equipped with belted tires. We record its fuel economy over a test. Then what we want to do is using the significance level alpha equals 0.05, and then the method of critical values to do hypothesis testing. We want to test for a difference in the fuel economy between the radial tires and the belted tires. We want to test if there is any difference between these two types of tires in the fuel economy. And then we will also construct a 95% confidence interval for the true mean difference due to the tire type. Because it is matched pairs data, everything comes in pairs. So the first thing we do is to get the DI, the difference. Then we can calculate the sample mean of the difference. And the sample standard deviations, and we can also call it standard error of this difference. The hypothesis we have here is H naught mu D. The true mean difference is 0. So there is no difference between these two types of tires. And the alternative is that there is some difference. Mu D is not equal to 0. And alpha is 0.05. The test statistic we use is this. Okay. Because the sample size is n equals 12, it is a small sample size. So by assuming H naught is true and D1 to D12 are ID normal, then the test statistic is a T random variable with degrees of freedom 11. And since the alternative is that mu D is not equal to 0, so that means the absolute value of the test statistic is larger. It provides us more evidence for the alternative. So we will reject the null hypothesis if the absolute value of the test statistic is greater than this critical value. A two-sided test, we use a 1-alpha over 2 quantile. And The observed test statistic is 2.48, and the critical value is 2.2. So the observed test statistic, the absolute value actually, is greater than the critical value. Then we reject H naught. We reject H naught. So we say that there is enough evidence to conclude that the fuel economy differs between radial tires and the belted tires. There's enough evidence for the alternative hypothesis. And two-sided 95 confidence interval is just using the formula for the one sample 95% confidence interval. If it is so because it's a two-sided, then we use a 1/2 quantile, and we plug in the sample mean and the sample standard deviation. Now it is for both of them are for the differences. Then this is our 95% two-sided confidence interval. And we see that the 95% confidence interval does not contain zero. So it coincides with the hypothesis testing result. We can actually also use this confidence interval to reject the null hypothesis. And the interpretation of the confidence interval of this result of the confidence interval is again like this. We are 95% confident that for the car type studied, the radial ties get between 0.0166 and 0.2674 more in fuel economy than the belted tires. Okay, this is how we interpret the confidence interval for the difference. We say that this tire is between this and this number more in fuel economy than this belted tires because it is a confidence interval that does not contain zero and it is positive. Okay, this is another example, a wood product example. So what we did in this test is we have two measurements for each wooden piece. There is a leading edge and also a trailing edge measurement made on each wood piece. This is our data. We have 5 observations. So the question is the leading edge measurement different from the trailing edge measurement for a typical wood piece? And we will do a hypothesis test with alpha equal to 0.05. And we will also make a two-sided 95% confidence interval for the true mean of the difference between these two measurements. Okay. So because it's a matched pairs data, the first thing we do is obtain the differences, 5 differences, and we obtain a sample mean and sample standard deviations, d bar and st. The parameter we made inference on is mu d, the true mean of the differences. Then we do the hypothesis testing. The null hypothesis is mu d is equal to 0, no difference. The alternative is mu d is not equal to 0, we have some difference. The significance level alpha is set to be 0.01. This is the test statistic. Sigma d is unknown, and sample size is small. We only have 5 samples, and we have only 5 observations. So we assume that these 5 observations are independent or on the same normal distribution. Then the test statistic will be following a t distribution with degrees freedom of 4. Since the alternative is mu d is not equal to 0, so we can measure how large the difference is to 0 using mu d minus 0, the absolute value of mu d minus 0. So there should be more evidence supporting the alternative when the d bar minus 0 is large. So this is an estimator. D bar is an estimator of the true mean mu d. There should be more evidence for HA if this is large. So that means there should be more evidence for HA if the absolute value of t is larger, because the absolute value of t is nothing but this the absolute value of this divided by a number. And we will reject h naught if absolute value of t is greater than this critical value. Then we plug in the data. We have the observed test statistic, and we also have the critical value. The value of the test statistic is 0.78. It is less than the critical value, so we fail to reject h naught. So there is not enough evidence to conclude HA. There is not enough evidence that the leading edge measurements differ significantly from the trailing edge measurements. So you always say that if there is enough evidence or there is not enough evidence for the alternative. In this case, you should not say that the leading edge measurements and the trailing edge measurements are the same. So just interpret the results using the context, translate the HA. And the 95% confidence interval, again, is like this. We use 1 minus alpha over 2 quantile. And we obtained an interval containing 0. Same for, so it should contain 0 because we failed to reject the null. And we are 95% confident that the true mean difference between these two measurements is between these two numbers. Okay, so that's all for the matched pairs data. And then we have a two-sample inference. Today we will see the large sample case. It is also the inference for the mean difference, or difference of the means. So we are comparing two means from two distinct populations without pairing our individual measurements. So this is what we did. We have two populations. And we have two samples. So the population mean for these two populations are mu1 and mu2, and we use the samples from each population to estimate these two population means, and we make inference about the difference between these two population means. Here are some examples of the two sample data. Set scores for high school A versus high school B. So two samples are from high school A students and high school B students. Severity of the disease in women and men. So these women and men are our two populations. Heights of New Zealanders and heights of Ethiopians. People in two countries are two populations. Coefficients for friction after wear of sandpaper A versus sandpaper B. So these two sandpapers provide us also two different populations, and we collect samples from these two populations. Here's a notation for the two sample inverse. The sample sizes for each of them are N1 and N2. They are not necessarily the same. And the true means are mu1 and mu2. And we use x1 bar and x2 bar, the sample means, to estimate the true means. The true variance are sigma 1 squared and sigma 2 squared. And sample variances are s1 squared and s2 squared. So x1 bar and x2 bar are estimates for mu1 and mu2, and s1 squared and s2 squared are estimates for sigma 1 squared and sigma 2 squared. In the large sample case, when ny and n2 are both greater than 25, then we will test this h0, mu1 and mu2. The difference of these two means is equal to a number against some alternative hypothesis. So the alternative is also about mu1 minus mu2. So it is either different, greater or equal to that number. And if sigma 1 squared and sigma 2 squared are known, then we will use this test statistic. Under the null hypothesis, and sample 1 points are ID with mean mu1 variance sigma squared, sigma 1 squared, and sample 2 points are also ID. And this test statistic Z would be a normal distribution. So this is because this is also due to the CRT, also the property of the normal distribution. Because by CRT, we know that x1 bar, the sample mean, we have a normal distribution with mu1, and the variance is sigma 1 divided by n1. And x2 bar also will be a normal with mean mu2 and sigma 2 squared divided by n2. Then what is the distribution of x1 bar minus x2 bar? This thing is a linear combination of two normal random variable, and it would be a normal distribution random variable with mean mu1 minus mu2, and the variance is sigma 1 squared over n1 plus sigma 2 squared over n2. So you can check the comments about the multivariate normal I posted in the announcements on campus. So this is how you get the distribution of linear combination of the normal random variables. So based on this, you will then know x1 bar minus x2 bar minus mu1 minus mu2 over the square root of this variance, which is a standard deviation, will be normal 0, 1. Okay, since we are assuming h0, so mu1 minus mu2 is just this number. That's why the test statistic is a standard normal distribution. So this is when you know the true standard deviation for both of the population. Then the two-sided or one-sided confidence intervals will be like this. This is the estimate of mu1 minus mu2. We have z quantiles, and when it is two-sided, use 1 minus L over 2 quantile, and if it is two-sided, use 1 minus L over quantile. And this is also a standard deviation, but it is standard deviation of x1 bar minus x2 bar. And if the sigma 1 and sigma 2 are unknown, then we will replace the sigma 1 and sigma 2 using S1 and S2. So the confidence intervals are like this. Everything are the same except that we use S to replace sigma. And let's look at an example. So we are, so a company is trying to find a workable geometry for some molded pieces of solid. And this company is doing a comparison between the weight of this specific shaped molded pieces that could be poured into a standard container. And we made a lot of this kind of molded pieces of this particular geometry and poured it into a standard container and measured the weight. And the comparison is between the weight of this specific kind of molded pieces with the weight of irregular shaped pieces that could be poured into the same container. And the irregular shaped pieces obtained is sort of crushing. Okay. So for each kind of pieces, we have 24 observations. So there are 24 weights measured for the crushed pieces and the molded pieces. And we use mu1 to denote the true mean packing weight of the crushed pieces, and the mu2 to denote the true mean packing weight of the molded pieces. And we want to formally test the claim that crushed one are greater than the molded one. So we are trying to do this. This will be our alternative. Okay, so we first state the null in the alternative. The null is that mu1, mu2 are the same. mu1 minus mu2 is 0. And the alternative is that the crushed packing weight is bigger than the molded packing weight. And for the example, we will be using the p-value. So this step is optional. This is test statistic. 0 is a number in the hypothesis testing. Here N1 and N2 are both 22. They are both smaller than 25, but we will still be using the normal distribution as a reference distribution because both of them are 22, so there should be no big problem using the CLT. And of course, we will be assuming that they are both IID for population 1 and population 2. And under these assumptions, the test statistic will be in standard normal distribution. And we calculated the observed test statistic, and we calculate the p-value. The p-value is the probability of C, this is the standard normal random variable, greater than the observed Z. Why? Because now the alternative is mu1 minus mu2 greater than 0. That means mu1 minus mu2 minus 0 should be large if the alternative is true. So x1 bar minus x2 bar. So this is the estimate of mu1 minus mu2. x1 bar minus x2 bar minus 0 should be large. So that it can support and can provide more evidence for the alternative hypothesis. This is what we have in the denominator of the test statistic. So that means we should have a large test statistic to support HA. Okay, that's why more extreme values for the observed test statistic means that a larger value than the observed test statistic. So it is probably to the right of the observed test statistic. Okay, and the probability we have is 1 minus phi of v is 1 minus phi of 18.3, which is an extremely small number. And with the p-value of this extremely small number, this is optional, we can already reject H naught because there is a very big evidence since the value is so small. So there is overwhelming evidence that more crushed solid material by weight can be poured into the container than the molded solid material. Okay, the packing weight, the mean packing weight of the crushed phases is greater than the packing weight of the molded pieces. And the 95% confidence interval, of course, is a one-sided confidence interval. It is just like this. We use the 1 minus alpha. And what we have is 42.4. This is a lower bound. So we say that we are 95% confident that the true mean packing weight of crushed solids is at least 42.4 greater than that of the molded solid. Okay, this is how you interpret the confidence interval or the difference. And if you look at the visualization of these two samples, here we use a standard leaf plot. You see that the molded one is different from the crushed one, and the crushed one is obviously bigger in value than the molded ones. It is making a lot of sense for us to get such kind of hypothesis testing and confidence interval results. Okay, and another example is about the anchor boats. We have two types of anchor boats with two diameters. One is boats whose diameter is 3/8 inch, and another kind of boats is the boats with 1/2 inch diameter. And the 1/2 inch ones, we collected 88 of them, and the 3/8 one, we collected 78 of them. And we measured the shear strength in KIP for each of these boats. Okay, and we want to compare the shear strength be between these two kinds of bolts. We use sample 1 to denote the 1/2 diameter bolts, and sample 2 to denote the 3/8 inch diameter bolts. Significance level of alpha is set to be 0.01. Of course, if we use a p-value, this is optional. And we will need to find out if the 1/2 inch bolts are more than 2 kip stronger in shear strength than 3/8 inch bolts. So that means the alternative would be mu1 minus mu2 is greater than 2. And we'll also calculate and interpret appropriate 99% confidence interval to support this analysis. Okay. So in 1/2 inch bolts, we have 88 of them. In the 3/8 one, we have 78 of them. And we calculate the sample mean for both of them, and also this sample standard deviations for both of them. The hypotheses are the null hypothesis, mu1 minus mu2 is equal to 2, and the alternative is that mu1 minus mu2 is greater than 2. If you are using p-value, then this one is optional. The test statistic is this. Assuming H0 is true and sample 1 point, so the 1/2 inch bolts measurements are RID observations, and the sample 2 are also RID. Then the test statistic Z should be following a normal distribution. And in this case, because the alternative is mu1 minus mu2 greater than 2, and there is mu1 minus mu2 minus 2 greater than 0. So because the alternative is like this, that means if we get x1 bar minus x2 bar minus 2 large, then we will support HA. Okay, that means because it's just the denominator and the numerator, sorry. So that means the Z test statistic will support the alternative if the test statistic is large. So the more extreme value of test statistic than observed value means that we should have a larger test statistic than the observed one. So it is probably to the right of the observed test statistic. And the observed test statistic is 3.84. Then we calculate P of Z greater than Z. And it is 1 minus phi of Z. This is the phi of Z. Phi of 3.84. And it is a value that is very close to 0. So since the p-value is so small, so close to 0, then we can reject H0. There is overwhelming evidence that the 1/2 inch anchor bolts are more than 2 kip stronger in shear strength than 3/8 inch bolts. And to be more accurate, you can say that in mean shear strain because we are doing the inference for mu1 minus mu2. And the one-sided confidence interval is a lower bound because we the alternative is this mu1 is greater and the lower bound is 2.35. So 2 is not contained in this 99% confidence interval. So this supports the previous analysis. So at significance level alpha equals 2.01, we can also reject the null based on this confidence interval. And the interpretation would be we are 99% confident that the true mean shear strength of 1/2 inch anchor bolts is at least 2.35. At least 2.35 is the translation of this confidence interval, KIP, more than the true mean shear strength of the 3/8 inch anchor bolts. Okay. So when you do the interpretation of the confidence interval for the difference, you should always say that which one is more than which one by how much. So let's say P1 at least so this is depending on the confidence interval. So this is how you do the interpretation of the confidence interval of the difference. Okay, so that's all for this video. And next time we will do the two-sample inference for the small sample case.